Okay. I'll jump back and hit the rest of the mathematical induction if we have time for it. So recall writing a sum or difference of rational expressions as a single rational expression. So basically adding two rational expressions together. We'd start with something like this. We'd get a common denominator, the new numerator that goes with it, distribute, combine like terms, maybe try to factor and simplify at the end. Well, in calculus, we need to be able to reverse this process. And this is something really that we need for Calc 2, that if we're starting with something that looks like this to do integration, which is what you do for like all of Calc 2, it's much easier if you have two simpler fractions than one combined larger fraction. The process of figuring out what two fractions added together to be equal to a rational expression, that process is called partial fraction decomposition. Each one of the little fractions is a partial fraction. All right, partial fraction decompositions can be written for rational expressions of the form P of x over Q of x, where P and Q have no common factors and the degree of P is less than the degree of Q. That's important. The only time we can do partial fraction decomposition is when the degree of the numerator is less than the degree of the denominator. And you got to make sure that it doesn't simplify. So there's 4 different cases. I'm going to do 4 different examples. Our 4 different cases is that the denominator is a product of distinct linear factors. Our second case is that the denominator is a product of linear factors, but some of them might repeat. Third, our denominator has prime quadratic factors, none of which repeat. And then our last case is if our denominator has repeating quadratic factors and repeating prime quadratic factors. That's important because if it's not prime, you're going to factor it and end up with, case 1 where you have a product of linear factors. Each of these 4 cases has a unique setup. They all kind of follow a pattern, but then once you get rolling, once you get the setup, they're all exactly the same. So here are our steps. We're going to set up the partial fraction decomposition with unknown constants, A, B, C, whatever, in the numerator on the composition. We're then going to multiply both sides of the resulting equation by the LCD. This will clear all our fractions. Then we'll simplify the right-hand side of the equation by distributing, combining like terms, that kind of thing. We'll write both sides in descending order. We're going to factor out any kind of x variable that we have. We'll equate coefficients of powers of x and equate constant terms. And then we will have created a system of equations that need to be solved. So you're going to solve that system by whatever technique, and then lastly, we're going to substitute the values for ABC, which is whatever we got, whatever the variables were in the very first step that we did, and these are going to be the answers from the system of equations, and then we'll plug that into our step 1, and we'll have our partial fraction decomposition. And all those steps are going to make so much more sense when we actually do a problem. So let's go with the first case where the denominator is a product of distinct linear factors. And I feel like all this looks so crazy, but I'm just going to tell you words and then it will make it better. All right, so this is where our denominator can be rewritten as the product of different linear factors. So maybe we have, well, yeah, I guess there it is. We'll just do this one. X minus 2 and x plus 1. The only way, so if this is the result of adding 2 fractions together, the denominators of the 2 fractions we added together, one of them is going to have to be x minus 2 and the other one's going to have to be x plus 1. And then we add those together and get this LCD. So every linear factor you have in the denominator is going to be its own fraction. So we're going to take our original explain to my kid he cannot hang on my right arm and I still be able to write. All right, so this is going to be equal to two fractions added together, one having a denominator of x minus 2 and the other having a denominator of x plus 1. All right, so if your denominator is a linear factor, we always need the degree of the numerator to be less than that. Denominator is linear, we need to be less than that. That means that our numerator has to be a constant. And that's what's being said up here. These capital A's, notice that there is no variable with it. And our variable is x, which I know can be confusing because you look at that and you're like, oh my God, there's variables everywhere. But keep in mind that our variable is x. So my numerators need to be a constant. I'm going to use a for this one. I can't use a second time, and I don't like to use the subscript like your book does. So I'd rather use different variables. So I'm just going to use a and b. So that means that this fraction over here is the result of these two fractions over here being added together. Now we just have to figure out what the numerator values are. And the way that we're going to do that is by, well, first, is there any questions on the setup? All right, so now we're going to multiply this entire thing by our LCD. And our LCD is x minus 2 times x plus 1. And we're distributing this to both sides and each term on each side. On the left, the whole denominator cancels out and we're left with 5x minus 1. And then on the right, we're going to have a times x plus 1 plus b times x minus 2. Really, after you get that initial setup where you have like your a's and your b's and stuff, everything that we do moving forward is the same for every single case, for every single example. You multiply through by the LCD. Then we're going to clean up this right-hand side by distributing. We look to combine any like terms, but there aren't any like terms. So now what we're going to do is we're going to rewrite our right side in descending order. And remember, your x is your variable. The a and b, those are just constant values that we're going to figure out. So when I rewrite it in descending order, I'm going to have ax plus bx plus a minus 2b. Next, we want to factor out any x's. So notice that these two have a like term of x, so we want to factor the x out. But when I write this, usually we put a GCF in the front. I'm going to put it in the back and rewrite this a plus b times x. And then this a minus 2b, since they don't have any x's with them, I'm kind of going to group them together. Any questions on what I've done so far?
Yeah, why do you put the x in the back again?
Well, I'm going to show you. It'll be clear in the next step.
Oh, okay.
Because our next step now is to equate our coefficients. If these two sides of, we have an equation, which means I got one thing equal to another thing. If they're equal, notice that the 5 here is the coefficient of the x term on the left. Well, now a plus b is the coefficient of the x term on the right. That leads us to the conclusion that 5 has to be equal to a plus b. So I just like to have like the coefficients in the front so it's easier for me to equate them. And then similarly, -1 is the constant on the left side. This a minus 2b is the constant on the right side. Therefore, we can conclude that -1 has to be equal to a minus 2b. Jordan, does that clear it up? I want the x in the back so that it looks like the other side.
Yeah, that makes sense.
Now we want to solve this system of equation and do it however you like. I think I'm going to do substitution method, although addition would be pretty easy too, but I'm going to do substitution. 5 minus 5 minus b is equal to a. So now I can take this and shove it in there. So -6 equals -3b, so b has to be equal to 2. And then a is 5 minus b. So we get a to be equal to 3. And then once we've solved our system, we're almost done. We just need to write our last like line. And what we're going to do is simply take the a and the b value and plug it into this first equation that we wrote in the very beginning, and that's going to be our partial fraction decomposition. So our final answer is 5x minus 1 over x minus 2 times x plus 1 equals 3 over x minus 2 plus 2 over x plus 1. And you can always check yourself by adding the two little fractions together. Questions, anybody? All right, let's try another one then. Let's move on to our second case. So our second case, we still have linear denominators. However, this time it's possible that we have a repeating linear denominator. So like if we ended up with this common denominator of x times x plus 7, see, we don't know. It could have been we had a fraction with a denominator of x and then one that had x plus 7 squared, or we could have had a denominator of x, a denominator of x plus 7, and then a third one with a denominator of x plus 7 squared, right? Either one of those additions, we're going to get an LCD of x times x plus 7 squared. And because we don't know which it is, we kind of have to account for the worst case scenario. We have to account for this one. And if there is no middle term, we'll end up with a numerator of 0. So what we're going to do when we have this repeating linear factor is you're going to start, so here it has ax plus b to the n, you're going to do ax plus b to the first power. And then the next fraction, it's going to be to the second power, and then to the third power, and so on until you get to whatever that exponent of n is. Now, I'm going to keep the exponent pretty low, otherwise we're going to get a system of equations that's like terrible to solve. By the way, I love how I'm talking into my headset, and my headset is not plugged in. So now I'll be nice and loud. Okay, so this one has a repeating linear factor and a non-repeating linear factor. And since the denominators are linear, we are going to use constants in the numerator. 3x squared plus 49 over x times x plus 7 squared. So first I'm going to deal with the linear factor that's not repeating. It's just going to be x. And we know that the numerator has to be a lesser degree, so this has to be a constant. And now, dealing with that repeating linear factor, we're going to take it to the first power and then to the second power. And if that had been to the fifth power, we would have done to the first, second, third, fourth, and fifth power. Not taking into consideration that it's repeating, all these factors in the denominator are linear, so all of the numerators have to be constant. So don't get thrown off, because I know technically this denominator is quadratic because we're squaring it, but the factor in the denominator is linear, and that's what we're going off of. One less degree than what the factor is, not the outer exponent. Questions on the setup? All right, and now everything else is like the same. We're going to multiply through by the LCD. That's going to give us 3x squared plus 49 equals a times x plus 7 squared plus b times x plus 7 plus c times x. Now we want to distribute on the right-hand side. Notice that we have a binomial squared there that you're going to need to write twice and multiply out, or use our shortcut. First one squared plus twice the product of the two terms plus the second one squared. Distribute my A. All right, now we want to rewrite our right side in descending order, like grouping our x squared terms, our x terms, and our constant terms. So I got my two x squareds here, and I like to cross them out as I go. And I was making the very last video of this whole course for my virtual class, and I didn't cross out, and of course I made a mistake. I just let it roll though. I just corrected myself so I didn't have to re-record. But seriously, I recommend you do it because it's easy to miss one, especially as the problems get, a little bit longer. So then these are my x terms. Oh, see, I almost missed an x term, plus cx, and then plus 49a. All right, so now we want to, any questions so far? All right, so we want to factor out any x's. And again, I'm going to factor it out to the back. here's just my constant term. If you notice on the right-hand side, I have x squared x and a constant term, but on the left side, I don't have a linear x term. So what we want to do here is put in a placeholder of 0x, and then we can equate our coefficients again. 3 is going to be equal to a plus b. 0 is going to be equal to 14a plus 7b plus c. And 49 is going to be equal to 49a. So we're going to equate these, write up our system of equations, and then solve that. So a plus b equals 3. 17a plus 7b plus c equals 0. And then 49a is equal to 49. And we solve. I think this is actually the hardest part of the whole thing, because sometimes we get these systems of maybe like 4 equations and 4 variables that can be tough to solve. But this one's nice. So from our bottom equation, we can get that a is equal to 1. Plugging that into our first equation, we then get b is equal to 2. So really, it's only this third one we need to work. It's 14 times 1 plus 7 times 2 plus c equals 0. So what's that? C equals negative 28. And now that we have our a, b, and c, we want to write our final fraction, partial fraction decomposition. Three x squared plus 49 over x times x plus 7 squared equals 1 over x plus 2 over x plus 7 plus a negative 28 over x plus 7 squared. Now you could put that minus in between the two fractions instead of in the numerator, but I typically put it in the numerator, because just like when you have like the remainder when you're dividing, sometimes our numerator is actually going to be a binomial, and if that's the case, then you need to like factor it out of multiple terms. So just be careful with that. Hold on one second, I can get my kids' Zoom meeting out of here. All right, any questions?
Yeah, I have a question. Like, how do you, when you have like a plus b equals 3 and then your other like equations there, how do you solve for those individual ones again? Like, how do you solve for b and a?
Okay, well, I started by solving for a, because 49a equals 49.
Oh, okay.
So I
So you
can conclude that a equals 1, and then I took that 1 and I plugged it into here for a, and then subtracted it from both sides and got b equals 2.
Oh, okay. So you
Sorry,
gotta,
I
all right,
skipped steps there.
cool. All right.
Anybody else? All right, so that's how we deal with the linears. It's always going to be a constant in the numerator. Now, the next two cases, we're going to move on, and our denominator has prime quadratic factors that aren't repeating. Well, it's like, I feel like it's a natural extension. So it's the same idea. Each factor becomes its own fraction, its own denominator. And our numerator always has to be a lesser degree than whatever our denominator was. So when we had a linear factor in the numerator, in the denominator, our numerator had to be a constant. Well, now when we have a quadratic factor in the denominator, that means that our numerator is going to be linear. So that's why we're seeing this ax plus b in the numerator. So that's the only difference. So 9x plus 2 over x minus 2 times x squared plus 2x plus 2 equals, and now make sure when you're given a problem like this that you check to make sure that your quadratic factor can't be factored, because if it can, you need to factor it down into the linears and work it with the linears. Otherwise, you're not giving me the most decomposed answer as you possibly can. Okay, so those are my two denominators. This one's linear, so its numerator has to be a constant. The next one's quadratic, so its numerator has to be linear. And again, we don't want to be reusing variables, so we're going to write this bx plus c. And now we proceed like we do every other one. We're going to multiply through by the LCD. This turns into 9x plus 2 equals a times x squared plus 2x plus 2 plus, now careful here, we're going to have our numerator bx plus c times x minus 2. Be sure to put that bx plus c in parentheses because we're going to have to FOIL that out. So we get ax squared plus 2ax plus 2a plus bx squared minus 2bx plus cx minus 2c. Now it's time to get organized, writing our right-hand side in descending order so that we'll be able to factor out our x's. Okay, and that's everybody. Now we will factor out our x's. So this is a plus b x squared plus 2a minus 2b plus c times x. And then 2a minus 2c is our constant. Anybody any questions so far? Now it's time to equate coefficients. You'll notice that we have an x squared term on the right, but not on the left. So again, we'll have to put in a placeholder, 0x squared, and now we can equate. 0 is going to have to be equal to a plus b. 9 is going to have to be equal to 2a minus 2b plus c. And then 2 has to be equal to 2a minus 2c. And then we solve the system. This one is not going to be as easy as the other ones. I think I'm going to start with some kind of substitution. I would like to be able to solve these two together, but that means I need to eliminate b. So what I'm going to do is I'm going to take this first one and say b is equal to negative a. So I'm going to substitute that negative a in here for b so that those bottom two equations only have a and c, and then I can solve the system of two. So this is going to give me 9 equals 4a plus c. And this one stays 2 equals 2a minus 2c. I want to use the addition method, so I guess I'll multiply the top one by 2, and then c's will fall out. Oh, 20 equals 10a, making a equal to 2. I see that b is equal to negative a, so that means that b is going to have to be negative 2. And then lastly, we need to solve for c, so I guess I think I'm going to just plug into the bottom equation. So 2 is going to be equal to 2 times 2 minus 2c. We get c to be 1. I do. I think that's the hardest part of the whole thing is solving the system. Any questions on the solving? All right, well, let's write our decomposition then. Nine x plus 2 over x minus 2 times x squared plus 2x plus 2 is going to be equal to 2 over x minus 2 plus a negative 2x plus 1 over x squared plus 2x plus 2. And here's our answer. This is a great example about what I was talking about earlier, that if you wanted to put the minus here, you would actually have to factor the negative out of this entire numerator and change it into 2x minus 1. So I just never do. I just leave it in the top. Questions at all? All right, last case coming up. Our last case is when we have a repeating prime quadratic factor. So we're just combining the ideas of case 2 and case 3. In case 3, we learned that if our denominator has a quadratic factor, our numerator has to be linear. And in case 2, we learned that if you have a repeating factor, you're going to do the factor to every power until you get to that given power, which happens to be 2. Again, we're going to keep it small so that we don't have some horrific system of equation that takes us an hour to solve. So anybody feel like they can give me the setup on this one? Be brave. Anybody got an idea?
I think that the denominators would be x squared plus 4, and then plus x squared plus 4 squared.
That's perfect. And since our denominator is quadratic, that means that our numerators have to be linear. Ax plus b and cx plus d. And now we'll multiply through by the LCD, clean it up, organize it, equate coefficients, solve a system, and rewrite. So I'm gonna put you guys in groups so that you can try working on that.
Yeah.
So you see that they really are all very similar, like the solving process. It's just the setup that can be unique. And of course, I'll probably only get to put one of these on the final, so I'm probably going to choose one that has a linear factor, a quadratic factor, and something that repeats. Just so that that gives me the opportunity to test as many cases in one problem.
Mm.
Hey, I do have a question about the final.
Yeah.
So I seen the review packet was like a load of questions.
Please don't be like my virtual students asking me if 97 questions are going to be on there.
I'm just well.
Of course not. It's going to be like 30.
Okay, I'm just checking.
Yeah, I'm going to put 97 questions on there.
Well,
What, I've been known to do that? What does that mean?
I don't know. I've taken some of them quizzes.
Yeah, but that's not in a timed environment.
That's true.
So, yeah, that's on my agenda. Well, it better be because, finals start Monday, that I got to make these 3 finals in the next few days. I will say I think that the final will be end loaded, especially since now, like when it's a paper test, sometimes I'll give you guys up towards 3 hours to take it, and I ask as many questions as I feel like it. But I feel like in this environment especially, I'm going to stay strict to that 2 hours, and I got to end load it. Like the last chapters have to be the most important part. So more than a third of the test will be from the last third of the course.
Ooh, limits.
Because you've already taken a final for 103, you've already taken a final for 104. I want to make sure that you really got the new stuff down. So. All right, I'd like to go back and do one more mathematical induction. If nobody has any questions about the partial fraction decomposition. And I think I want to do the one that is on page 354 because the other one I have a video for. But I don't have a video for the one on 354. But this way you've at least seen a second proof live. I'd encourage you to watch the video for the other one. All right. So our proof starts with a show line. We need to show that S sub 1 is true. So basically, we just plug 1 into our formula here on the right and see if we get 1/6, which is our first term. So S sub 1 is equal to 1 over 2 times 1 plus 4. And there's our 1/6. So we've shown that this is true. Next, we want to assume that S sub k is true. And what that means is that S sub k, which is equal to 1 over 2 times 3 plus 1 over 3 times 4 plus 1 over n plus, I'm sorry, that should be a k. K plus 1 times k plus 2 is going to be equal to k over 2k plus 4. So basically all we've done is plug k in for n in this initial thing that we're trying to prove. After assuming that this is true, we want to show that s sub k plus 1 is true. So that means that we want to show that s sub k plus 1, which is equal to 1 over 2 times 3 plus 1 over 3 times 4 plus 1 over k plus 1 times k plus 2. Now remember, that's the kth term. That's not the kth plus 1 term. Here's the k plus 1 term. Right, because it's going to be k plus 1 plus 1. K plus 1 plus 2 is equal to k plus 1 over 2 times k plus 1 plus 4. And I would clean this up a little bit on the right-hand side. All right, this is 2k plus 2 plus 4. So we're saying that this needs to be equal to k plus 1 over 2k plus 6. So that's what we're trying to show. So we're going to start with our s sub k plus 1. It's 1 over 2 times 3 plus 1 over 3 times 4 plus 1 over k plus 1 times k plus 2 plus, and I'm going to clean up this next term here. 1 over k plus 2 times k plus 3. Everything but the last term right here is equal to s sub k. Right? Looks just like this. So what we're going to do is we're going to substitute this in its place. Oh, s sub k plus 1 becomes k over 2k plus 4, and then we still have this last term plus 1 over k plus 2 times k plus 3. We want to add these two fractions together. We'll have to get a common denominator, so we factor our denominators. S sub k plus 1, our common denominator is going to be 2 times x plus 2 times k plus 2 times k plus 3. So this numerator becomes k times k plus 3. And then here's our LCD, new numerator of 2. Now we're ready to put it together. S sub k plus 1 is going to be equal to, I'm going to distribute my numerator while I put it together in one fraction. K squared plus 3k plus 2 all over 2 times k plus 2 times k plus 3. Yeah, and see, I just took a quick glance back up to see what am I even trying to get to, right? Right, we're trying to get to this. See, that 2 in the denominator made me nervous for a second there, but now I see that there is a 2 here. In fact, I may even want to think about this in the factored form in the denominator. So this leads me to believe I need to factor that numerator, and a k plus 2 should cancel out. So s sub k plus 1, factoring this numerator, sure does factor into k plus 1 times k plus 2. And those k plus 2's cancel out, giving us s sub k plus 1 equal to k plus 1 over 2 times k plus 3. And that's what we were trying to get to. All right, we said that was what we were going to show, that s sub k plus 1 was equal to that. So that means that, yeah, this is going to work. We just need to write our wrap-up statement. Therefore, by mathematical induction, S sub n equals n plus 1 over, hold on, oh, that's not right. I need to write this here. Okay, so S sub n is equal to n over two n plus 4 for all integers n. And there we go. Questions? Yeah, I know, that takes some practice.
I could barely keep up
Well, then why don't you tell me to slow down?
because
Like, no news is good news. I'm rolling.
Are there going to be a couple of these on the homework that we can work on then?
Yeah, I can't
Okay.
imagine I'm gonna find one that's good for the final though. I mean, how do I put this on my math lab? Really?
Yeah.
So honestly, I don't know if it's even on the homework. Maybe, but how do I put this on there? Just, I couldn't even put trig identities on there.
Gotcha.
This is not the most important thing in the course.
Okay.
I would not kill myself on this. Now, if you got discrete to take, or you know, depending on who you're taking calc with and how much they love proofs, fine, you might have to see it, but probably not.
does Rob like proofs?
Rob does like proofs.
Oh my god.
But I don't remember ever proving anything by induction in calculus, because this is really more, yeah, I don't think you're going to see this. Maybe in discrete, since it's a proof writing course, which teaches you a bunch of different techniques for writing proofs, but. Okay, let me just say, I'm not putting this on the final. I'm just making that decision right now.
Thank you very much.
Yes.
My hero.
Because again, I don't know how could I possibly do this on my math lab? It's on the final in person, but I don't know how to do this with my math lab. But practice it so you can have it right on the take-home quiz. If there even,
When's-
well, now I don't even know if there was one on the quiz. Anna, you've been working on the quiz. Is there even one on the quiz?
No.
No. Well, there you go. So I'm sure you'll study it a lot. That's
Well,
right.
I gotta. If I'm gonna be in calc.
Well, there are a few in the homework, my math lab. They
Okay.
have like some weird way to do it, but